Hi everyone, welcome to the session on secondary index storage, Plasma, designed to scale. I am Durga Akhil Monroy, software engineer in the storage team at Couchbase, and I'll take you through this session. The index service enables query to perform scans with high throughput and low latency, and Plasma manages the data stored in the indexes. In this session, we'll go through how Plasma manages memory and disk resources. We'll also go through some scaling aspects and improvements in the 7.0 release. Let's get started with a brief overview of Plasma's design. Plasma is the underlying key-value storage engine for the index service. It supports both range scans as well as point lookups. Plasma is built using a lock-free data structure, which not only enables highly concurrent index updates, but also scales with high number of CPU cores. It uses a lightweight snapshotting mechanism to eliminate any locking during concurrent scans. Memory management is done through LRU-like eviction algorithm. This concurrent design results in high throughput on scan workloads, especially when they have high locality. Plasma's underlying disk storage is an append-only log-structured persistent storage, which is optimized for SSDs and NVMe. Plasma uses a non-blocking incremental disk compaction and also achieves fast recovery using checkpointing. There are a lot of tunable knobs in Plasma, and they are auto-tuned based on workload, memory, and index keys to provide optimal performance. Now, let's take a look at how Plasma manages memory. Memory usage in Plasma can be broken down into a few categories. The bulk of the usage comes from cached index keys. Then, there is some usage from the internal data structure and related metadata. The work buffers and internal memory fragmentation also contribute to the usage. The index service memory quota limits the memory use for the index keys and is honored on a best effort basis. To adhere to this quota, Plasma will evict index keys from memory, which causes the index resident percent to reduce. Plasma uses 90% of the index memory quota, and the rest is used by the indexer to maintain index lifecycle. Since the memory quota is not a hard limit, Plasma's memory usage can be more than the quota. So it is suggested to have some headroom between the quota and the total system memory. Sometimes there may be some unexpected memory consumption in the system. Let's see how Plasma handles these situations. The memory tuner is a component in Plasma that dynamically adjusts the Plasma memory quota in order to create more memory headroom. It counteracts memory use due to fragmentation and other processes external to the indexer and Couchbase by reducing the quota. This helps to avoid out-of-memory scenarios. The memory quota is tuned by looking at system metrics, and the algorithm is based on feedback control systems. The metrics which the tuner looks at are the system free memory and the indexer process resident memory. If the tuner finds that there is less free memory, or if the indexer process memory is too high, then it will decrement the quota. This results in creation of headroom by evicting more resident data. Additionally, during the step, retained freed memory is forced back to the OS. On the other hand, if there is sufficient headroom, then a quota will be incremented slowly back to its original value. We've seen what consumes memory and how the quota changes. Now, let's take a look at how the quota dictates the index resident percent and what Plasma does to keep memory use in check. Eviction frees index keys present in memory to bring the resident percent down. If any of these index keys are being that are being evicted are not on disk, then they will be written to disk before being evicted. Of all the index keys in memory, Plasma has to choose which of them to evict. For this, an LRU-like algorithm is used to evict index keys that have not been accessed recently. Eviction has many triggers. It's mainly triggered through the swapper, which is a background component that evicts pages. The swapper does two types of eviction: burst eviction and periodic eviction. Burst eviction comes into play only when the usage is above the quota and evicts pages to alleviate memory pressure. Periodic eviction runs continuously in the background and sweeps index keys so as to determine and maintain the working set. The other trigger for eviction are the scans and mutations. If there is memory pressure, scans and mutations are slowed down and eviction is done to bring memory usage down. Periodic eviction determines the working set of index keys to keep in memory. The rest of the index keys are candidates for eviction. Data accessed in the last 10 minutes is treated as the working set. This 10 minutes is called the sweep interval. If the determined working set does not fit in quota, the sweep interval is proportionally shortened. With a shorter sweep interval, more recent data is classified as the working set and retained in memory. This enables exploitation of temporal locality of queries. If the determined working set fits in quota, then Plasma will preemptively evict data to create headroom below the quota for sudden allocations that are caused by bursty traffic. This eviction runs till memory usage is 50% of the quota and only runs if the index is expected to not completely fit in memory. Now, let's move on to how Plasma manages its disk resources by looking at log file management. For persistence of data to disk, Plasma uses an append-only log-structured store or logical log file. It is a contiguous 64-bit logical log space. The log head and tail represent the current active range of log space being used and can be used to determine the disk space usage. The log head is the offset of the first byte of data, and log tail is the offset of the last byte of data in the logical log. The logical log is divided into a list of 4 GB physical files, and each file maps to an offset range in the logical log space. Since the logical log is append only, as new data is written to disk, the log space grows. This causes the log tail to advance. If a 4 GB threshold is crossed, then new physical files are added. Plasma stores index keys in sorted order and manages them in ranges. These index key ranges are called index pages. As new data is added to the index and written to disk, index pages may get rewritten. New index pages are appended to the logical log, and rewriting can invalidate existing pages. This adds to the stale data on disk. Index pages are rewritten to speed up index scan by reducing the I/O ops needed to read a page. This rewriting happens when index pages are compacted and during full persistence of index pages. Both of these operations are proportional to the mutation rate. The index fragmentation ratio is the fraction of stale data on disk, and it depends on the mutation rate. With higher mutation rate, more data can get stale and cause the disk fragmentation to increase. To tackle this fragmentation, Plasma has a background routine called the log cleaner. The log cleaner does disk compaction to reduce fragmentation. The log cleaner works by reading index pages from the logical log from head to tail. If it sees a stale index page, it is removed from the logical log by advancing the head. If the cleaner sees a valid page, it is rewritten and the head is advanced. As the logical log is compacted by the log cleaner, the underlying disk space can be returned back to the file system. If a physical file has some valid data and no stale data, it can be shrunk by performing hole punching. If a physical file no longer has any valid data, then the file is deleted. Hole punching provides a more fine-grained control in this case. This disk compaction is incremental in nature and happens in the background. Plasma will try to maintain 30% fragmentation, and the cost to perform log cleaning is proportional to the mutation rate. If the mutation rate is very high and the log cleaner is not able to run fast enough, the fragmentation can increase. If it increases beyond 80%, then writes are throttled to allow the log cleaner to catch up and keep the disk space usage in check. A few more details about hole punching. Hole punching enables Plasma to return disk space to the OS without deleting the whole file. It causes the file size to shrink. The stale data is hole punched after disk compaction only if the physical file has some valid data in it. There must be at least 64 MB of contiguous stale data to hole punch. Plasma will perform hole punching only if the underlying file system for the index data supports it. This is checked at indexer startup, and generally network and encrypted file systems do not support hole punching. In such a case, Plasma will just wait till a whole file contains only stale data and deletes it. Let's now briefly go through some scaling challenges in Plasma. With collections in Couchbase Server 7.0, Plasma had to undergo significant changes to scale to 10,000 indexes. These are some of the challenges that were solved in Plasma to achieve this scale. Each index runs eviction independently and does not factor in the usage of other indexes on the node. A hot index could evict unused data from a cold index. This reduced the effectiveness of Plasma's caching. The dedicated buffers and threads allocated by each index resulted in high memory and CPU overhead. With large number of threads, other problems like thread limit become more easy to hit. Each index had its own logical log, and with a large number of files, not only is there high I/O overhead, but the I/O performance also degrades with highly concurrent traffic. To overcome these scaling challenges, Plasma's resource management was made more efficient and now works across indexes. The broad solutions were to share resources across indexes and also to improve utilization and efficiency. With shared resources, the resources are now assigned and reclaimed from indexes on the fly based on demand. The resource allocation is also elastic. The utilization and efficiency has also been improved such that the overheads are not proportional to the index size or the number of indexes. Overall memory and disk I/O overheads have also been improved. With these improvements, GSI can now support 10,000 indexes on collection in 7.0. To facilitate the sharing of resources, Plasma now groups indexes into shards. Each shard functions as a unit and consolidates various resource management lifecycles. All the indexes in a shard share a swapper, which is used for eviction, and also share other background worker threads. These instances also share a buffer pool. The logical log or LSS is now shared and stored and stores data from multiple indexes so that the number of physical files being operated on is limited. Many enhancements were carried out to improve the resource utilization efficiency, and some of them are: improve the bulk data load with Bloom filters, a self-tuning periodic eviction, opportunistic page compaction, and incremental checkpointing for better recovery. Now let's take a deeper look into the I/O and recovery improvements. Bloom filters were added to Plasma to improve bulk loads or insert-heavy workloads. Mutation processing has two steps. First, a lookup for the old index key value must be performed, and this old value has to be deleted. Second, the index key value must be inserted. When the mutation being processed is an insert of a new index key, there is no need to do a lookup for the old key value. To help with this, Bloom filters were introduced as a way to track index key values on disk. A Bloom filter is a space-efficient probabilistic set data structure. If the old index key value is not in the Bloom filter, the lookup for the old key value from disk can be skipped. This reduces the I/O required for that lookup, and in general reduces the random I/O traffic in insert-heavy workloads. To provide this functionality, Bloom filters consume memory. The memory usage depends on a few things, like the number of items in the index resident percent, and the configured accuracy of the Bloom filter. By default, the Bloom filters are disabled and can be turned on and tuned using indexer settings. With the default configuration, for every item on disk, Bloom filters consume approximately 5 bits of memory. Plasma implements multi-version concurrency control, or MVCC, for supporting index snapshotting for stable scans. Due to this, Plasma has to maintain old values and new values for index keys, as well as deleted index key values all at the same time. When these old or deleted index key values are no longer needed by any active snapshot, they can be resolved by performing page compaction. This helps to preserve memory and disk space and also reduces the I/O needed to read or write page to disk. Prior to 7.0, this compaction was done only when a page had accumulated some n number of mutations. To perform compaction, a page must be fetched into memory from disk, and this can be expensive. Therefore, from 7.02 onwards, page compaction has been made opportunistic to take advantage of the page lifecycle when it is naturally brought into memory. This means that it can be performed efficiently without incurring additional I/O. Some of these are when a page is split upon becoming full, when a frequently modified page is written to disk, during incremental disk compaction by the log cleaner, and when a page with a lot of unresolved old or deleted values is scanned. The indexer creates a disk snapshot or persistent checkpoint every 10 minutes to facilitate crash recovery. A checkpoint saves index metadata for fast recovery. Prior to 7.0, full checkpoint were persisted. This includes new mutations since the previous checkpoint and metadata for all index pages. The indexer creates a disk snapshot or persistent checkpoint every 10 minutes to facilitate crash recovery. A checkpoint saves index metadata for fast recovery. Prior to 7.0, full checkpoint were persisted. This includes new mutations since previous checkpoint and metadata for all index pages. Persisting all metadata was proportional to the index size and is expensive. 7.0 onwards, the metadata persistence has been made incremental so that its cost is proportional to the mutation rate instead. This reduced the CPU and IO usage with a large number of indexes, and especially for cold indexes whose mutation rate was low. All the incremental checkpoints are saved to a log-structured store, similar to how index key values are written to disk. With this, recovery involves reading index metadata from all incremental checkpoints and rebuilding the index using the most recent metadata. To summarize the improvements, this graph shows the improvement in disk bandwidth utilization during index maintenance or incremental index build. In red is Couchbase Server 663 and in blue is Couchbase Server 702, which has all the improvements. We can see that the disk utilization has reduced from around 50% in 663 to around 20% in 702. Now let's take a quick look at some stats and their meanings and what you can look out for while monitoring them. First is the resident ratio. It represents the fraction of index keys present in memory, and it depends on the index quota and the working set being maintained. It's recommended that 20% resident ratio is maintained for all the indexes. If the resident ratio goes too low, the mutation and scan processing can slow down due to increased disk I/O, and the memory quota must be revisited to be increased. The next stat is the index cache miss ratio. It's the fraction of needed index keys that were not in memory. It is a measure of the effectiveness of Plasma's caching. If high, it indicates that more disk I/O was needed and that the working set does not fit in memory. If to make this better, you must revisit the queries and sizing so that more of the working set can be cached. The index data size. It's the size of the data in the index, uncompressed and not including any metadata and overheads. It's the latest set of data that is being managed by the indexer. The index disk size, on the other hand, is the size of data on disk, which is compressed and includes metadata and overheads like stale data. If the disk size is large compared to the data size, we have to check if hole punching is supported and if fragmentation is being kept in check. Coming to fragmentation, it's this percentage of stale data on disk. Ideally, Plasma will maintain this close to 30%, but if it rises to around 80%, then the mutation rate can be artificially slowed down, and this has to be taken into consideration. Higher resident ratio leaves more bandwidth for disk compaction to keep the fragmentation in check. Thank you.